Hi, lucky you. You get to look at my beautiful visage for another fascinating leap into the world of kinematics. I want to review what parametric versus non-parametric means, because what we're after is in trajectory motion, two-dimensional motion in the x direction and the y direction. We're having a particle being shot, say from a cannon or a bat hitting a ball. We're going to get a parabolic trajectory, and we're interested in how far from where we launch the object, how far from where we launch it, it lands. And so I want to review what it means to be in parametric form, because that's actually what we've been using for x and y. Remember, parametric means that there's a parameter, I'll call it theta here. You go into the black box, the equations, and out comes x and y. So maybe x is the cosine of theta, and y is the sine of theta. Theta is the parameter. It gives us x and y. But if I square x and I square y, and that would mean squaring y, that x squared plus y squared, sine squared plus cosine squared, is the Pythagorean identity, is a unit circle. It equals 1. This is non-parametric form. It does not involve theta in any way. Non-parametric form means I come in with x and I can figure out y. So, if x were 0.5, I could come in with 0.5, square it, and get 0.25, and then y squared would be 1 minus 0.75, and I'd have to take the square root of 0.75 to get the answer, 0.8 something, no doubt. So again, here's a parabola in parametric form. The parameter is t, that y is a function of t and x is a function of t. So you give me t and I'll tell you what x and y are. Very similar to what we did with our launching of the object in 2D motion. You give me the time and I'll tell you where the object is in terms of x and y. So, for example, if t were 1, x would be 1 minus 1 for 0, and if t is 1, 1 plus 2 is 3, squared is 9, so I know that 0, 9 is on the parabola. So that's going through the parameter of t. Non-parametrically, y is equal to, say, x plus 3 squared, and that gives us, because I solve for time here, x is time minus 1, so time is x plus 1. So if I put in x plus 1 plus 2, I get x plus 3 for what y is squared. And so this is the non-parametric form for y. You give me x, I give you y. In the parameter form, you give me t, and I give you x and y. So that's just a review, because that's what we're going to do with this. Here is one of our big four equations, that y, or d, equals negative 1/2 gt squared plus v0t. Remember, I'm defining my launch as v taking place at some theta, and this is the x direction and the y direction. So in the x direction, it's whatever this component of the vector is in the x direction. And remember, we remembered alphabetically, x goes with cosine. So this is v cosine theta, and in the y direction, that's v sine of theta. And we can make use of those because these are the parametric forms. You tell me the time, and we can find out where x and y are here. So this would be, you give me time, and I figure out x, and I figure out y at a particular time. But I can't take x and immediately tell you what y is, because it's in parametric form. The reason that there's a negative sign here is that the initial velocity is upward, so up is positive, Gravity acts downward, so therefore G is negative 10 meters per second squared. So I'm going to take X, which is a function of my parameter T, and I'm going to solve for T by dividing by V cosine theta, because this is V cosine theta. That's V in the X direction times time. So divide both sides, and I get this is my parameter time. Let's plug that in here, which means we have to square this and put it there, and then take this and put it there. So I did that here. So negative 1/2 G T squared X squared over V squared cosine squared theta. Remember, cosine squared theta is the cosine of theta squared. It's not the cosine of theta squared. We don't square the angle and take the cosine. We take the cosine and then square the answer. That's what this notation means. And when I plug in X over V cosine theta here, I get V in the Y direction, which is V sine theta, times T, which is X over V cosine theta. And remember, sine theta over cosine theta, you might remember, is tangent of theta. Good to know. So I have Y equals negative 1/2 G X squared over V squared cosine squared theta, that's T squared, in non-parameter form, plus the tangent of theta times X. So now I can continue to do my operations and say, where is Y 0? Because when we start at 0, our range lands at 0. So I want to set Y equal to 0 to find out where it lands. When is the object at 0 in the Y direction? Well, when I factor an X out of this, I get X equals 0. No kidding. At the beginning of time, the object's on the ground. That's called the no-duh solution. The other one is where I factored out the X and got negative 1/2 G X over 2 V squared cosine squared theta, plus the V's canceled, and I got tangent of theta as sine over cosine. The X has been factored out. So when this is 0, that's going to be this point over here. You don't have to derive this. Just follow me, because we never have to derive anything on the SSAT. We just need to memorize about 50 formula to get our 800, and this is one of them. The big 4 and this range equation. So if I solve this for X by moving this to the other side and then multiplying by 2V squared cosine squared theta and dividing by G, if I go through all of that, I will get this equation for range. Extra special bonus points if you happen to remember that 2 times sine theta cosine theta is the sine of 2 theta. And so it's easier to write this equation by saying V squared sine of 2 theta over G. That's the range. Remember, we got 870 as our range before when V was 100. G is 10. Let's see, we had theta was 30 degrees. I don't want to get a negative value, so I'm going to use the absolute value of G in this equation for the range. And so I have 2 times V squared, and that's this V here, 100, not the X or Y V's, times the sine of theta, which with 30 is 1/2. The cosine of 30 is the square root of 3 over 2. And I want to divide all of this by G, which is 10. So these 2's cancel. This 2 moves to the bottom. I get 20. And I get 100 squared, which is 10,000. divided by first 10, so that makes it 1,000, and then another 2 makes it 500 root 3. Root 3 is about 1 3/4. So we multiply 500 by 7/4. So 500 by 7/4 is 800, about 850. Well, it's actually more like 4 goes into 30, 7 times? Almost 8. So it's somewhere between 870 for the range and 880, which is what we got before. So this equation is really, really important, that v squared sine 2 theta, and you'll have to remember that the sine of 2 theta is 2 sine theta cosine theta, that this gives you the range as long as you're on level ground. No shooting things off a cliff. Do I have, I'm looking to see if I have a problem set up here, and I don't. I just have a sort of review of it, and there's nothing wrong with quick review before we go on and do an example. So here again is the review of when we launch something at a velocity, we break it up into x and y components, and when we're looking for the range, we use this equation here, or this one, if we remember that the sine of 2 theta is equal to 2 times the sine of theta times the cosine of theta. So if someone comes, and we don't even have to know necessarily what theta is, if someone comes along with a 3, 4, 5 triangle, a famous right triangle from our SAT days, and says that the sine equals 0.6 and the cosine equals 0.8, then if we want to know what the sine of 2 theta is, it's 2 times the product of these two. So 0.6 times 0.8 is 0.42, and 0.42 times 2 is 0.84. So sine of 2 theta is 0.84. I didn't even have to know what theta is, let alone what 2 theta is. I can still use this range equation because I know that the 0.84 can be plugged in here times v squared over g. So memorizing this equation for the range on a level surface, again, it must be ground level. We can't be shooting off a cliff. So absolutely no fair using this equation if this is the case, because you're not landing on this level. You're surpassing that level and falling to the ground. So the downtime is going to be larger than the uptime. We'll do those problems, but right now we just want to add this equation to our big 4 so that we stay focused on the bare bones minimum equations that we need to have at our fingertips to solve these problems in under 60 seconds and grab our 800. Let's do some examples, okay?